Okay, so first I'd like to thank the organizers for inviting me to this beautiful place. So I'll talk about two aspects of homology and expansion on random complexes. Okay. So the plan is as follows. We'll first talk about random Cayley complexes. We'll recall the Alon-Reuchman theorem for Cayley graphs and introduce or recall, should I say, the concept that come into the generalization to higher Cayley complexes. And the second topic would be, how do I put the point into? Thank you. And then we'll talk about another model for random complexes. This is joint work with my student, Omer Muyal. And so it's another model for simplicial random complexes. We'll talk about the structure, how to pick them up randomly, and the main result would be the probability that they are connected for some big R. Okay, but let's start with this. And I assume that everybody knows by heart all these basic definitions, but let me go over them quickly. So suppose we have a graph, undirected, simple, with n vertices. The Laplacian is the V cross V matrix that has the degrees on the diagonal and the -1 in place UV, where UV is an edge and 0 otherwise. And the eigenvalues of the Laplacians are, the first one is 0, corresponding to the all one eigenvector, and lambda 2 is our spectral gap, of course plays a crucial role in everything concerning the graph. So the spectral gap measures how connected a connected graph is. So we have we start with a connected graph, but we want to say something quantitatively about this connectivity, and so lambda 2 is just this number. What are Cayley graphs? Cayley graphs are constructed as follows. We have a finite group. We have some symmetric subset of the group. So the S is S minus 1. And the Cayley graph is the graph on the vertex set, which is G. And the edges are just X, Y, where Y, X is just in G, and Y is X times S, where S is in the generating set. So for example, the cycle, the n cycle is the Cayley graph of Zn, the integer mod n, with generating set plus minus 1. This is written additively. And the cube is C of Z2 to the n with the unit vectors as the generating set. Okay. Now, the Alon-Reuchman says the following thing. Take any group of size n and pick randomly a subset of size log G times some constant, which depends on how good the expander we want to get. Then lambda 2 of this Cayley graph will be at least 1 minus epsilon times m. M is, of course, the maximal eigenvalue that we can get, the maximal lambda 2 that we can get. If you take log G elements, then you almost surely will get as lambda 2 the maximal eigenvalue, almost maximal eigenvalue. So this is the result that we want to extend to high dimensions. And for this, we will need first a generalization of lambda 2, and secondly, a generalization of what's a Cayley graph. So we'll need to talk about Cayley complex. One should say that this is essentially best. Constant here is the best. There is a well, a conceptual improvement due to Landau and Russell and Low and Schulman, which says that the log G factor can be replaced by log D of G, where D of G is the sum of the degrees of the complex irreducible representations of G. Since D of G and G are, well, D of G is at least a square root of G, so it doesn't really make a very strong difference, but nevertheless, it's a nice formulation. Okay, so first we need the generalization of lambda 2. I actually believe that that it was covered, everything was covered in the last week, but I'm not sure, so we'll go over it very quickly. So suppose we have a simplicial complex and we have some fixed abelian group. We denote by Ck of x. This is the space of k cochains. Let's take R to be the reals, but it doesn't matter at this point. So Ck is the skew symmetric maps from xk. Here xk is really the k simplices. So subsets of size k plus 1. And the skew symmetry means that the sign of phi changes according to the order of the vertices. And we have the coboundary operator from Ck to Ck plus 1, but just declaring dk phi at the k plus 1 simplex to be the alternating sum of phi at the faces of this simplex. And again, notions that we have encountered even today. Zk is the space of k cocycles, so it's the kernel of dk. Bk is the image of the k minus 1 cochains. These are the k coboundaries. Zk contains bk. This is the what was called the orthogonality relation. And the reduced cohomology group of X is just the quotient Zk by Bk. Okay, so now we focus on coefficient, on real coefficients. And for real coefficients, we can define an inner product on Ck by just taking the usual standard inner product between vectors. So phi dot psi is just a sum of phi sigma, psi sigma, where we sum over all k simplices. Sometimes people put some non-zero coefficient, positive coefficient here. For our purpose, this is not needed. And this inner product defines an adjoint from Ck plus 1 to Ck. It's simply the adjoint matrix of dk, the transpose of that matrix. This is the formal definition. And finally, the Laplacian, the K-Laplacian, which generalizes that one Laplacian that we actually the zero Laplacian that we talked about earlier, the graphical Laplacian, is a map from Ck to itself, and it's the sum of going this way, so dk star dk, plus dk minus 1, dk minus 1 star. This is a positive semi-definite operator from Ck to itself. And this is, of course, this was defined in the earlier 20th century by topologists. And they proved, let me say, well, a few more definitions. The kernel of this Lk are all k cochains, such that both dk phi and dk minus 1 star phi are 0. So on both directions, we get 0. And the simplicial Hodge theorem, or the baby Hodge theorem, says that the kernel of Lk is isomorphic to the K homology with real coefficients. In our context, this is just very simple linear algebra. In the continuous context, this is a bit of, needs quite a bit of analytical work, and certainly non-trivial. It's called the Hodge theorem, of course. And what is the equivalent of, or the high-dimensional version of lambda 2? It's mu k of x. It's the minimal eigenvalue of Lk. So note that, and this is called the k-spectral gap of x. Note that if the minimal eigenvalue of Lk is 0, then the kernel is non-trivial, and therefore we get a non-trivial kth homology. If the kth homology, cohomology, is non-zero, then we can ask so the kth homology, if the kth homology is 0, then the minimal eigenvalue is positive, and then it somehow measure how 0 is this 0. So actually, Nati has a way of saying how 0 is this 0. So assuming that this is 0, how strongly it is 0. In Hebrew, it sounds a little bit better, but this is actually the, I think, the philosophy, so to speak, of this expansion question. You have a discrete phenomenon, so saying whether HK is 0 or non-zero, and if it's 0, you want to measure how 0 it is, or how far it is from something that has a non-trivial homology. In any case, so this was a bit of philosophy, but in any case, mu k is the thing that we want to bound. So actually, mu 0 is lambda 2 of the one skeleton, and mu k is positive if and only if hk is 0. Okay, so we have one ingredient of one generalization of lambda 2, and now we need a generalization of the Cayley graph. And I'm sorry? Yes, that's correct. But this is a bit, okay. So going back to the philosophy, this is a bit more complicated because in graphs, there is only one notion of connectivity. So in high-dimensional complexes, you can ask, the complex can be trivial in different ways. It can have 0 real homology. It can have 0 Z2 homology. It can be even trivial homotopically. All these are different, certainly different concepts. So when you ask about trigger, then I answered for the real, for having 0 real homology or cohomology.
Maybe a silly question. Is there a reason the LK is defined on both sides, adding just one side?
Yes, because because otherwise we will not have this. Yeah. Yeah. What happens here is that actually, lambda 2 was defined only on one side because actually mu 0, you see mu 0 is the minimal eigenvalue of the zeroth Laplacian. The zeroth Laplacian is not exactly the graph Laplacian, it's the graph Laplacian plus the J matrix, the all one matrix. Okay, in any case, we need to talk about Cayley complexes. So here we first define the complete balanced complex. This actually appeared in the Pavel talk. We take k+1 copies of G. We review each copy as a zero-dimensional complex with a discrete set of G elements, and we take what's called their join. I'll show you a picture in a minute. And it turns out that this join is homotopy equivalent to a wedge of spheres, to a bouquet of spheres. So we have many spheres connected at one point. The number of spheres is just bits, n-1 to the k+1. And okay, let me show you the picture. We have these copies, and we declare the maximal simplices to be in the full join to be all multicolored simplices. Now, for the Cayley complex, the balanced Cayley complex, we have a subset. This is the generating set, so to speak, A. And we take YAK to be the K-dimensional complex that contains a full K-1 skeleton of YGK. And the K simplices are just Y1 to YK plus 1, whose product in the right order, Y1 to YK plus 1, belongs to A. So the product has to belong to A. Clearly, if we take any choice from K, just K of the copies, we can complete it in A ways to get a full K simplex. Oh, just because what I said is that actually when you can define the maximal simplices to be all these, and then automatically the full K-1 skeleton is contained in that. You can always complete it in A ways. Yeah. Okay. So what do we get out of this construction? Well, we do get interesting things. For example, we get the torus. If we take G to be Z3, we take A to be 0, 1, and so YA2 would be T. So here I drew it. The color classes are the colors, right? So we have 0, 1, 2, 0, 1, 2, and the green one is 0, 1, 2. And you can see that, so this is a simplex because 0 plus 1 plus 2 is 0 in Z3, so it belongs to A. On the other end, 0 plus 1 plus 0 is 1, so it also belongs to A. So we get that torus. So you can get interesting things out of this construction. And, oh, okay, so small remark, what happens if A is a subgroup? Well, it turns out that if A is a subgroup, what you get is a bunch of spheres of both dimension K-1 and K. So you get gamma 0 SK-1s and gamma 1 SKs, and where these are the numbers. Okay. Now we have only the ingredients for a higher Alon-Reuchmann. So the higher Alon-Reuchmann will say that if we take A to be a subset of size log of DG, where D is the sum of the degrees of the irreducible representations of G, then the probability that mu K-1 will be less than the maximum value, which is M, will be less than 1 minus epsilon times M is negligible. So this is really a direct, a sort of extension of Alon-Reuchmann, and it's best possible in the sense that if we take, because there are groups that are not generated by less than log DG elements. If we take a group which is, if we take less than log DG, then we don't generate the whole group, and therefore automatically, because of what we said earlier, beta of K-1 will be non-zero, and therefore the lambda will be mu of K-1 will be 0. So there is no chance that something like that will be true. So this is indeed best possible. Okay, so I think I have a few minutes to. It is not restricted at all. Any finite group. Right, indeed, okay. For the abelian case, there is something that you probably know called sum complexes. So, but this works for any group. Okay, so a few words about what goes into the proof. So first we call the Fourier transform of the non-abelian one. Suppose that we have a function from G to the complex numbers, and we have a representation. So a representation meaning just there is an action of G on GLDC on C to the D. So it's a function from G to GLDC, the Fourier transform of f at the representation rho is simply the combination of the rho x's with coefficients f of x. So of course, if you know the abelian Fourier transform here, what we have are numbers. These are the characters. And we get the usual Fourier transform. In the case of a non-abelian one, rather than the characters, we have the full representation. Okay, and now we define mu of A to be the, we take the Fourier transform of the characteristic function of A, so simply the sum of rho of A, where A belongs to A, and we take the spectral norm, and we take the maximal spectral norm over a non-trivial irreducible representation. You see, the hope is that if A is random enough, then, and R is non-trivial, then there will be a lot of translations here. Therefore, this will be small. This is the general philosophy of why Cayley complexes can be good expanders. So, because somehow when you take the Fourier transform of a 1A over a non-trivial character or non-trivial representation, you hope that it's somehow, if A is somehow a little random, then this will be small. And the theorem is that mu k minus 1 of this Cayley complex is at least A minus k times nu of A. So we hope that nu of A will be small, and therefore mu k minus 1 will be at least A minus a small thing. And remember that the maximal we can get is A, so that if mu of A is small, then you get an almost optimal high-dimensional expander, spectral expander. Okay, so this is the non-deterministic part. For in order to get the Alon-Reuchmann, you need, okay, I should say something. You need the spectral, the variational characterization of the spectral gap. And this is the Rayleigh quotient of the computing the spectral gap. And actually, it turns out that you can get something a little bit better. You can get a somewhat higher, bigger, well, so to speak, minimized over a smaller set, which is this. Namely, mu k minus 1 of y is the minimum of dk phi norm square over phi norm square, where phi is just in the kernel of a dk minus 1 star. And the point is how to estimate this. And for this, we have the Garland method. So the Garland method, basically, it's a very basic thing. It tells you that if you have a complex and say a dimensional complex, and you look at the links of k minus 2 simplices, these links are graphs. If all these graphs are very good expanders, then mu k minus 1 will be positive. This is the Garland, in general, it's many results. It was even mentioned under some different guys in the first talk today. In any case, Garland says that the minimum of dk minus 1 phi over phi will be at least k times lambda of x, where lambda is the minimum spectral gap of the graphical links, minus k minus 1 of m, where m is the number of the k simplices that contain the specific k simplex sigma. Okay, Garland result, this is a 72 paper in Annals. It used it to prove a conjecture of Serre on the cohomology of P groups. More recently, Garland method had many applications in combinatorics, and theoretical computer science, and I assume that was also mentioned a lot in the previous week. But in any case, once we have this, and we have this 5 minutes, right? Okay. Once we have this, and we have this, and we have this bound, then we are almost there. So first, we know that the links of k-2 simplices are isomorphic to just bipartite graphs, Cayley bipartite graphs, YA1. One can show that this lambda2 of the Cayley bipartite graph is at least A minus this mu nu of A. And then you apply the Garland bound, and you get that mu k minus 1 of YAK is k times lambda2 of the graph minus k minus 1A. But because lambda2 was at least A minus nu of A, we get that mu k minus 1 is at least A minus k times nu of A. Now, it turns out that for random A, you can make this very small. So I won't go through the details, but they are quite simple. But this will give us the along Rehovot. Okay, so but now I have a question. We were talking about mu k minus 1, which is the spectral gap. What about the coboundary expansion? So spectral gap measure how zero is the zero real homology. Now I want to ask how zero is the Z2 homology. So for this, assume that we've also met these notions. Suppose that we have a k Z2 cochain, so a function from the simplices to Z2. We define the Hamming norm simply to be the number of simplices where phi is non-zero. We define the cosystolic norm is the support, the minimal support of phi plus dk minus psi, where psi is in the ck minus 1 of x. So this is a kind of the natural, the right notion of the support of phi. Because phi itself can have a very large support, but when we modify it by a coboundary, its support will become very small. So this is phi of cosystolic, the cosystolic norm, and the coboundary expansion is the quotient of this dk phi over phi cosystolic. This is just a generalization of the Chigger constant. And now my question is, well, I have two conjectures. One conjecture is that actually what we proved for the spectral gap remains true for the higher Chigger constant. So there is some constants flying around, but if we basically take log of dg random elements from G, then the Chigger constant becomes strictly positive almost truly. Okay, so this is one conjecture, which is sort of a randomized conjecture about random things. A non-random conjecture would be that if you take, well, let SPQ be the, I should have defined it, but in any case, these are the generators, the LPS, Lobotsky-Phillips-Sarnak generators of Ramanujan graphs. Take these generators, take G to be PSL to FP, and take the Cayley complex that corresponds to this subset. Now, it stands to reason that HK minus 1 will again be bounded away from 0 by some absolute constant. Okay, so I'm sure that this conjecture is true and perhaps not very difficult, but for this conjecture this is not clear that why should this be true? Well, I leave it as a, yeah, I'm not sure. Maybe I should call it problem rather than a question. Yeah. This, if true, then I have no idea how to really approach it. There are constructions of subcomplexes with co-bounded degrees, so any of a balanced subcomplexes that have positive co-boundary expansion, but they are random. And this would be a non-random subconstruction, and it would be new and interesting, at least conceptually. I'm done. Yes. So, I actually, okay. So this is the second part of the talk, but this is, okay. Okay. Last slide, please. No, okay. No, I mean, no, not that I know. So, but there is for mu k minus 1, there is, and there is a natural bound, and actually it appeared in old paper by Lee, right? Right, there is, yes, and but yeah, but for the co-boundary expansion, well, we have barely one example of a co-boundary expander in 2 dimensions. So situation is really not very good. Yeah. Okay. It depends on A. So the degree is, okay, so first we are talking about the codegree. So the degree of how many full simplices contain a specific k-1 dimensional simplex. So this degree is simply the size of A. If A is bounded, then but it's not vertex degree bounded. No, certainly it's not a. Yeah. Yeah. Right. So. Yeah. No. So it's not. It's code degree are bounded, and but not the vertex degree are of course just square or something like that. Actually, n times A. Okay, n times the sum. Not bounded.
Maybe are there specific groups for which you can take A to be constant size? Is that known?
So
for the same kind of complex.
So I don't well. The group has to be such that it can support an bounded degree expander. So it cannot have a bounded derived length, for example. It cannot be solvable. So natural candidates will be.
The question is random.
No, a random set will not work, and it doesn't work even in the graphical case. The question is whether there is a constant.
Or some group, it doesn't.
No, okay. So we are mixing between two concepts. For spectral expansion, there is no problem. For spectral expansion, if you take a good expander, say the LPS expander, then it will also be spectral with a little bit somewhat different parameters. It will be a constant co-degree expander. This is no problem because of this bound that I mentioned. For co-boundary expansion, so this was the second conjecture. This is a conjecture. I have no idea if it's true or not.
Actually, I was asking about the spectral.
No, the spectral thing, there is no problem at all. Yeah, yeah.